Discovered asteroid impact crater in Australia that's billions of years older than dinosaurs. What if I told you that scientists just discovered a cosmic scar on our planet that's older than multicellular life itself? A crater so ancient it witnessed Earth when it was practically an alien world. The scientific community is buzzing with excitement over what might be the most significant geological discovery of the decade. Hidden in the rugged landscape of Western Australia's Pilbara region lies what researchers have now confirmed as the oldest impact crater ever found on Earth, a mind-boggling 3.47 billion years old. This isn't just breaking the previous record, it's absolutely shattering it by more than 1.25 billion years. To grasp just how ancient this crater is, when this massive space rock slammed into our planet, Earth looked nothing like the blue marble we know today. There were no trees, no animals, not even multicellular organisms. The atmosphere contained almost no oxygen, and the continents as we know them didn't exist. This crater formed during what geologists call the Archean Eon, a mysterious time period that represents Earth's tumultuous adolescence. The scale of this discovery is equally impressive. Initial estimates suggest the original impact structure may have stretched up to 100 kilometers across. That's roughly the distance from New York City to Philadelphia, carved out in an instant by a cosmic bullet traveling many times faster than a speeding bullet. Have you ever tried to imagine the raw energy released when a space rock the size of a small mountain hits our planet at over 40,000 miles per hour? The explosion would have dwarfed the combined power of all nuclear weapons ever created. What makes this discovery particularly remarkable is how it compares to other famous impact sites throughout Earth's history. The Chicxulub crater in Mexico, which famously contributed to the extinction of the dinosaurs, is a mere baby at 66 million years old. That's less than 2% the age of our Australian find. The previously considered ancient Vredefort crater in South Africa, recognized as the world's largest visible impact structure at around 2 billion years old, now seems relatively recent by comparison. Even the Yarrabubba crater, which was previously hailed as Earth's oldest at 2.2 billion years, has been demoted to second place. This new discovery predates it by more than 1 billion years, a time gap greater than the entire existence of complex life on Earth. When you think about it, more time separates this impact from the dinosaurs than separates the dinosaurs from us. Does that make your head spin a little? It should. Finding a crater this old required geological detective work of the highest order. After billions of years, most evidence of cosmic impacts gets erased by Earth's restless surface. Our planet is constantly reshaping itself through plate tectonics, erosion, volcanic activity, and countless other processes. It's like trying to find childhood footprints on a beach that's been washed by tides for thousands of years. The odds were stacked against this discovery from the start. So how did scientists manage to identify something so thoroughly weathered by time? The breakthrough came through a combination of cutting-edge technologies and good old-fashioned geological fieldwork. The research team from Curtin University employed advanced geological dating techniques, primarily focusing on analyzing tiny zircon crystals found within the impact site. These incredibly durable minerals are like natural time capsules, preserving evidence of the extreme temperatures and pressures experienced during the impact event. The scientists used a method called uranium-lead dating, which exploits the predictable decay of radioactive uranium into lead over time. By measuring the ratio of uranium to lead within these zircons, they can calculate on an extraordinarily precise age. Moreover, the team also identified what are known as shocked minerals, minerals that show distinctive patterns of deformation that can only occur under the extreme conditions of a meteorite impact. The most compelling evidence came from the discovery of spherules, tiny glass beads formed when rock is vaporized by an impact and then rapidly cools as it rains back down to Earth. Finding these microscopic signatures of an ancient apocalypse requires meticulous attention to detail and specialized equipment that wasn't available even a decade ago. The location of the discovery in the Pilbara Craton adds another layer of significance. This region of Western Australia is already famous among geologists as one of the few places on Earth where rocks from the Archean Eon are accessible at the surface. It's a geological time capsule that has somehow avoided the constant recycling that affects most of Earth's crust. The Pilbara is also home to some of Earth's oldest evidence of life, 3.5 billion-year-old stromatolites, fossil remnants of ancient microbial mats. Does this proximity suggest a relationship between cosmic impacts and life's early development? That's one of the tantalizing questions this discovery raises. What's particularly fascinating is that the crater was hiding in plain sight all these years. Generations of geologists have studied the Pilbara region, yet the true nature of this structure remained unrecognized until now. It's a humbling reminder of how much we still have to learn about our own planet's history. The quest to confirm this discovery was not without controversy. Initial skepticism from the scientific community required the research team to build an overwhelming case using multiple lines of evidence. After all, extraordinary claims require extraordinary proof, and claiming to have found Earth's oldest impact structure is about as extraordinary as geological discoveries get. Could there be even older impact structures waiting to be discovered? The search continues, but for now, this Australian crater holds the title of the oldest known scar from our planet's cosmic past. When this massive asteroid slammed into Earth 3.47 billion years ago, it encountered a world that would be utterly alien to us today. The Archean Eon represents one of the most mysterious chapters in our planet's history, a time when Earth was still finding its identity. Imagine looking up at a sky that wasn't blue, but instead had an orange-brown hue due to a methane-rich atmosphere with barely any oxygen. The sun, about 20% dimmer than today, would have appeared smaller and less brilliant through this hazy atmospheric veil. The continents as we know them didn't exist. Instead, the planet featured scattered archipelagos of volcanic islands and small proto-continents emerging from a vast global ocean that covered much more of Earth's surface than today. The Pilbara region itself was likely part of a small continental fragment surrounded by shallow seas. Within an ozone layer, harsh ultraviolet radiation bombarded the surface unfiltered. The landscape would have been barren of any visible life. No trees, no grass, nothing but bare rock, volcanic fields, and primordial microbial mats clinging to the edges of hot springs and shallow waters. When the asteroid struck this ancient landscape, the consequences were apocalyptic on a scale difficult to comprehend. Based on the crater's estimated size, scientists believe the impactor was likely between 5 and 10 kilometers in diameter, roughly the size of Manhattan. It would have been traveling at cosmic speeds of around 15 to 20 kilometers per second, over 33,000 miles per hour. The kinetic energy released upon impact would have been equivalent to millions of modern nuclear bombs detonating simultaneously. The immediate aftermath would have been catastrophic. The impact would have vaporized the asteroid itself, along with billions of tons of Earth's crust, sending a superheated plume of rock, vapor, and debris high into the atmosphere. This material would have rained back down across thousands of kilometers, potentially triggering widespread wildfires, though there was nothing but microbial life to burn. Immense seismic waves would have rippled through the planet's crust, triggering volcanic eruptions and tsunamis hundreds of meters tall that would have washed over any nearby landmasses. But it's what this impact reveals about Earth's early crust that has scientists most excited. The crater's massive size and depth provide unprecedented insight into the composition and behavior of our planet's outermost layer during the Archean. One surprising finding is that Earth's crust was already relatively thick and continent-like in the impact region, challenging previous theories that suggested Earth's earliest crust was uniformly thin and oceanic in nature. The chemical composition of the impact melt, rock that was liquefied by the extreme heat of impact and then rapidly cooled, offers a pristine sample of Earth's crust from 3.47 billion years ago. Analysis shows a surprisingly evolved composition with significant amounts of silica-rich materials, suggesting that processes similar to modern plate tectonics might have been operating much earlier than previously thought. This adds fuel to the ongoing debate about when Earth's distinctive geological cycle truly began. The impact site also presents a unique opportunity to study Earth's early atmosphere. When massive impacts occur, they can temporarily punch through the atmosphere, causing a partial vacuum that pulls air down from higher altitudes. As this air rushes back in, it can become trapped in cooling impact melts, preserving tiny samples of ancient air. Preliminary analyses of gas inclusions in impact-generated rocks suggest an atmosphere rich in carbon dioxide and nitrogen, with virtually no oxygen, consistent with what we know about Earth before the Great Oxygenation Event, which wouldn't occur for another billion years. Have you ever wondered what actually crashed into Earth all those billions of years ago? Was it an asteroid, comet, or something else entirely? Share what type of cosmic object you think created Earth's oldest crater in the comments below. This impact occurred during what planetary scientists call the Late Heavy Bombardment, a period when the inner solar system experienced an unusually high number of asteroid impacts. This phenomenon is thought to have resulted from gravitational disturbances in the outer solar system that sent a barrage of asteroids toward the inner planets. Finding a crater of this age provides crucial evidence that Earth was indeed affected by this cosmic bombardment, just like the Moon and Mars, where we can more easily see ancient impact scars. What's particularly fascinating is how this single event fits into Earth's broader geological record. The timing of the impact coincides with what geologists call the Paleo-Archean era, a time when Earth was beginning to develop more stable continental platforms. Some researchers speculate that massive impacts like this one may have actually contributed to continent formation by creating weaknesses in Earth's crust that later became boundaries between tectonic plates. The impact would have also had dramatic effects on Earth's heat budget. The enormous energy released would have melted thousands of cubic kilometers of rock. Once liquefied, this material would have circulated differently, potentially altering local or even global convection patterns in Earth's mantle. Some scientists suggest that major impacts could have triggered episodes of increased volcanic activity lasting thousands of years after the initial event. The environmental consequences would have been similarly far-reaching. Dust and aerosols thrown into the atmosphere would have created a temporary impact winter by blocking sunlight. This cooling effect would have been followed by extreme warming as impact-generated greenhouse gases like water vapor and carbon dioxide accumulated in the atmosphere. These rapid climate fluctuations would have created environmental stresses and opportunities that may have influenced the evolution of early life forms. Speaking of life, this is where the discovery becomes even more intriguing. At 3.47 billion years old, this impact occurred during a critical window in life's early development. The oldest definitive evidence of life on Earth comes from 3.5 billion-year-old microbial fossils found in, coincidentally, the very same Pilbara region of Australia. This means that simple life forms were already established when this massive asteroid struck, raising fascinating questions about survival and adaptation. Could the impact have temporarily sterilized large portions of Earth's surface? Absolutely, but it might have also created new habitats and opportunities for life. The hydrothermal systems generated by the impact, where hot fluids circulate through fractured rock, could have provided energy and chemical gradients ideal for certain types of microorganisms. Some researchers even propose that major impacts delivered essential volatile compounds or created complex organic molecules that contributed to life's early chemistry. By studying the precise timing of this impact in relation to evidence of early life forms, scientists hope to better understand life's resilience and adaptability during Earth's most violent epochs. The discovery might ultimately help answer one of science's most profound questions. How did life survive and even thrive on a young planet regularly bombarded by cosmic projectiles? This monumental discovery is fundamentally rewriting our understanding of Earth's geological timeline. For decades, scientists have pieced together Earth's early history using fragmentary evidence, isolated rock formations, mineral samples, and chemical signatures. Now, this crater provides a massive exclamation point in that timeline, a defining moment that helps anchor other discoveries in context. The preservation of such an ancient impact structure forces geologists to reconsider what other primordial features might still be detectable if we know how to look for them. The implications extend far beyond just cataloging another crater. This discovery suggests that Earth's early crust was surprisingly resilient, capable of recording and preserving evidence of catastrophic impacts despite billions of years of tectonic activity, erosion, and metamorphosis. It challenges the conventional wisdom that Earth's most ancient history has been effectively erased by our planet's dynamic geology. Instead, it appears that with the right techniques and locations, we can peer much further back in time than previously thought possible. For astrobiologists studying life's origins, this crater represents a crucial data point in understanding Earth's early habitability. The impact occurred during a time when life was just gaining a foothold on our planet. By analyzing how the local and possibly global environment changed following this massive impact, researchers can better understand the conditions under which early life evolved. The extreme energy of such impacts can create unique chemical environments, synthesizing complex organic compounds and establishing chemical gradients that primitive organisms might have exploited. Some researchers have even proposed the controversial hypothesis that major impacts might have played a direct role in life's emergence, creating the conditions necessary for simple organic molecules to organize into self-replicating systems. While this remains speculative, having a precisely dated impact from this critical period gives scientists a specific event to correlate with emerging evidence of Earth's earliest known microorganisms. The crater's discovery also forces a recalibration of impact frequency models for the early Earth. Most of our understanding of ancient impact rates comes from studying the Moon, where craters are preserved for billions of years in the absence of erosion, plate tectonics, and weather. Finding such an old crater on Earth provides a crucial ground truth data point that helps validate or adjust these models. If this crater survived, how many others from this era might also be waiting to be discovered? And what might their cumulative effect have been on Earth's early development? Perhaps most significantly, this discovery challenges the traditional view of Earth's early Archean period as a uniformly hot, toxic, inhospitable world. The preservation of this crater suggests a more complex reality, a planet already developing stable crustal regions amid the chaos, regions that would eventually become the nuclei of today's continents. The impact site itself may have created a unique ecological niche, with hydrothermal systems that might have harbored specialized early microbial communities. The research techniques developed to identify and date this ancient structure have implications that extend well beyond this single discovery. These methodologies can now be applied to other suspected impact sites worldwide, potentially unlocking a treasure trove of information about Earth's distant past. The multidisciplinary approach, combining traditional field geology with advanced isotopic analysis, mineral studies, and geophysical surveys, demonstrates how modern science increasingly transcends traditional academic boundaries. This discovery has significant implications for understanding similar features on other celestial bodies. Mars, for instance, bears the scars of countless ancient impacts, many dating back to the same early period as this Australian crater. By understanding how impact structures age and evolve on Earth under known conditions, scientists can better interpret similar features observed on Mars, Mercury, and other rocky bodies. This comparative planetology approach has already yielded insights into how impact craters weather differently under various atmospheric conditions. The innovative dating techniques refined during this research could potentially be adapted for future space missions. Imagine rovers or sample return missions applying similar methodologies to precisely date impact features on Mars or the Moon, creating a more accurate timeline of our solar system's turbulent youth. The lessons learned from identifying this ancient Australian crater might literally help us read the surfaces of other worlds. This discovery also transforms our understanding of Earth's remarkable resilience. Despite suffering an impact that would have been apocalyptic by any standard, releasing energy equivalent to millions of nuclear weapons, the planet's geological and potentially biological systems persisted and recovered. This has profound implications for understanding planetary habitability over long timescales, suggesting that life, once established, might be more tenacious than previously thought. For climate scientists, the crater offers a natural experiment in catastrophic environmental change. By studying the environmental aftermath of this massive impact, recorded in surrounding rock formations laid down in the following millennia, researchers can gain insights into how Earth's early systems responded to sudden, extreme perturbations. These lessons could inform our understanding of climate tipping points and planetary boundaries today. The crater discovery highlights how much remains unknown about our planet's most ancient history. For every question this remarkable find answers, it raises a dozen more. Future research will likely focus on establishing a more precise chronology of events surrounding the impact, what came before and after, how long recovery took, and what permanent changes it might have triggered in Earth's evolving systems. Advanced modeling techniques will allow scientists to reconstruct the impact in unprecedented detail, from the asteroid's approach to the final settling of ejected material. This computational approach, combined with continued field research and laboratory analysis of samples, promises to extract every possible bit of information from this extraordinary geological time capsule. Perhaps most exciting is the possibility that this discovery might inspire a systematic search for other ancient impact structures. If one such crater survived 3.47 billion years, others might too. A comprehensive survey using the techniques refined during this research could potentially reveal a network of ancient impact sites, allowing scientists to map the distribution and frequency of major impacts during Earth's formative years. As we continue to explore and understand our planet's deepest history, discoveries like this remind us that Earth's story is far richer and more complex than we once imagined. The scars of our planet's violent youth, preserved against astronomical odds through billions of years, continue to enlighten us about our world's remarkable journey and perhaps offer clues about the development of countless other worlds throughout the universe. If you've enjoyed this deep dive into Earth's ancient history, please hit that like button and subscribe to our channel for more mind-expanding science content. Share your thoughts in the comments. Would you want to visit this ancient crater site? And as always, stay insanely curious.